Good morning, class. My name is G. Gautami. I am from EC department. In our previous class, we have seen flipping circuits, comparators. Now, in today's class, we are going to study about two new diodes. Those are Zener diode and light emitting diode. Today, we are going to study about how Zener diode is going to work, BI characteristics of Zener diode, and why it is different from our PN junction diode, and we are going to study the construction of light emitting diode and what are the applications of light emitting diode. All these things we are going to study. Now first let us look into the different types of diodes. Now here we can see the different types of diodes. PN junction diode, LED, photodiode, Zener diode, tunnel diode. On the right hand side we can see the PN junction diode, LED, photodiode, Zener diode and tunnel diode. How these are going to look like in a practical scenario, that we can see in our right hand side. Right. PN junction diode we have already studied in our first class. Now what is today's topic? Our Zener diode and light emitting diode. Today we are going to study Zener diode and light emitting diode. Now, what is Zener diode? Why it is different from PN junction diode? That we are going to see. Here, Zener diode is a special type of diode where it is going to allow current to flow in a reverse direction also. Now let us recollect our first class. In our first class, what we have studied, diode is a two-terminal device and it will allow current to flow in only one direction, and it is going to oppose the current to flow in the reverse direction. This is what we have studied in first class. This is what happens in our PN junction diode. But whenever we are talking about Zener diode allows current to flow in reverse direction also. Now that is why we are naming our Zener as what? Special type of diode. Now let us see. This is a special kind of diode which permits current to flow not only in forward direction but also in reverse direction. Now let us consider a PN junction diode. If in reverse bias of a PN junction diode, if we increase the reverse voltage, what is going to be happening? At a particular level, at a particular voltage, our diode is going to what? Damage, or else our diode is going to break down. Right? That breakdown is known as what? Breakdown voltage. Now what in case of Zener? That we need to know. Now here we can see a normal diode when operated in reverse bias gets damaged. The reverse current passed above a certain value is passed through it. Now this certain value is called as breakdown voltage in case of any normal diode, say PN junction diode. Now what is going to happen in a Zener diode? When we have crossed some certain breakdown voltage in Zener diode, what is going to be happening? Let us see. Now whenever we are passing or exceeding the breakdown voltage of Zener diode, this Zener diode is going to allow the reverse current pass through it, right? Clear? And this voltage or this breakdown voltage is known as what? Zener voltage. We can see here. Let us see this ones. The breakdown voltage of a Zener diode is very low, but this diode allows the reverse current to pass through it. Once this breakdown voltage is exceeded, right now what I said, that I have put it in a slide. That breakdown voltage is called as what? Zener voltage. Now the question is why this is happening? Why it is happening? Because a Zener diode is heavily doped and it has a thin depletion layer, depletion region, right? Depletion region width is less and it is heavily doped. That is why we got this kind of characteristics or this kind of behavior of a Zener diode. Now what about PN junction diode? Our PN junction diode is lightly doped and depletion width is more compared to our Zener diode. This is the main difference. This is how we have categorized PN and Zener, and this is why we are calling Zener as what? Special type of a diode. Now here we can see the practical Zener diode on left hand side and the symbol of Zener diode on right hand side, and it has the anode and cathode. What is anode? Positive. And what is cathode? Negative. Yes, this is a basic which we have seen. In case of Zener diode, we have a control breakdown voltage, right? That we can see here. Hence, there is a control breakdown which does not damage the diode when a reverse current above the Zener voltage passes through a Zener diode. Now, this is what just now I said. A Zener breakdown occurs in a diode with heavy doping and thin junction, right? Whereas in our PN junction diode, what is going to be happening? It has lightly doping and the width of depletion region, that is D, is more. Now, a Zener diode in its reverse bias exhibits a control breakdown voltage and it allows the current to flow to keep the value of voltage across the Zener diode close to the Zener breakdown value. Now, if you want to write the equation for electric field, we can put it in this format. The electric field that occurs due to applied reverse voltage can be calculated as what? E is equals to V by D, where V is what? Reverse voltage and D is what? Width of depletion region in our Zener diode. Now here we can see the VI characteristics of a Zener diode. If we observe the VI characteristics of Zener diode, which is on right hand side, in forward region or in forward bias region, it just looks like a PN junction diode characteristics, right? Zener diode VI characteristics or Zener diode's behavior in forward bias condition is just similar to our PN junction diode forward characteristics. Now look at the reverse bias region. Now, whenever in a PN junction diode reaches breakdown, that means this is what we still here. Let me show it clearly. Now, if we consider PN junction diode, just will get our output in this format, right? Now, if it crosses this breakdown, what is going to be happen? Our diode, right? What is our diode? Our PN junction diode is going to damage, right? Clear? But take in case of Zener diode, what is going to be happen at this breakdown? Once this reaches this breakdown voltage, that is VZ, Zener voltage, what is going to be happen? You can see current is increasing, right? current is increasing. That is what makes the difference. That is what makes the difference between PN junction diode and the Zener diode. In Zener diode, what is happening till this point? Till this point, from here to here, right? From here to here, till this point, what is going to happen? You can see constant current. But once it is crossed its breakdown voltage, or as once it is reached VZ, here you can see increase in current. This is what we are talking about. This is what a Zener diode is going to allow current in reverse bias direction. Now, this is a Zener diode. It will allow current in reverse bias also. Right. Now, this is the VI characteristics of a Zener diode. You can see here. The VI characteristics of a Zener diode are common for any diode when operated in forward bias. Yes, forward bias, whatever VI characteristics will get, that is same as of our normal diodes, or same as of our PN junction diode. But the reverse bias operation of Zener diode makes it very important to consider. Why it is very important to consider? Because after VZ, we can see increase in the current. And this special character, this special VI characteristics of a Zener plays a very important role. This is why a Zener diode is very special. This is why a Zener diode is going to act as a voltage regulator. And by this phenomenon only, a Zener diode is used in voltage limiting circuits, right? And a Zener diode used for what? Voltage reference also, right? Now let us move on. The point where bent is shown in reverse bias operation. Bent, we have seen, right? This is the bent. Here we saw the bent, right? The point where the bent is shown in the reverse bias operation is the Zener breakdown voltage, after which the diode allows high reverse current through it. Have we seen? Yes, we have seen here, right? Now, the Zener voltage is indicated by VZ. Yes, here VZ is indicated. We already seen in this VI characteristics. Now, let us see what is avalanche breakdown, when it is occur and where it is occur. Avalanche breakdown occurs in a PN junction diode, which is moderately doped and has a thick junction. Clear? Avalanche breakdown, where it is happening? In our PN junction diode, and as it is moderately doped and its junction or depletion layer is more, that is why it is going to happen in a PN junction diode. Avalanche breakdown usually occurs when we apply high reverse voltage across the diode. Yes, in a reverse bias condition, what we are doing? If we are increasing the voltage constantly, whenever we are increasing the voltage, avalanche breakdown will occur. What is avalanche breakdown? Avalanche breakdown means where carrier multiplication will be done, then whatever the electrons present in the depletion layer, it's going to conduct. And this is why your PN junction diode is going to be conduct very heavily in reverse bias condition, which leads to what? Breakdown. So that is why we are not exceeding the breakdown voltage of a PN junction diode. Once we exceed, what is going to be happening? Avalanche breakdown will happen, and then our diode will not be useful for further use because it will be damaged. So as we increase the applied reverse voltage, the electric field across the junction will keep increasing. Due to this strong electric field, what is going to be happen? The electrons in the the electrons in the depletion layer is going to be conduct, and in our p side some minority carriers will be there, those are electrons, right? These are going towards the depletion layer, and these will collide with the electron present in the depletion layer. Now whenever this going and colliding with the electrons, bounded electrons which are present in the depletion layer, their carrier multiplication will be takes place. Whenever carrier multiplication is going to take place, this our diode is going to be conduct very heavily and is going to break down. This is known as what? This is known as what? Avalanche breakdown. Now, if the applied reverse voltage is VA and the depletion layer width is D, then the generated electric field can be calculated as what? E is equals to V by D. A is equals to VA by D. What is V here? The reverse voltage. And what is the D? Width of the depletion region. Clear? Is clear? Is this clear? Whenever we are increasing the applied reverse voltage, see, whenever we increase the V, what is going to be happen? Obviously, our electric field will also increase due to this strong electric field. Carrier multiplication will be takes place. Due to that, our diode is going to conduct very heavily and avalanche breakdown will occur. Right? Whenever it is going to occur, our diode will not be useful further because it is going to break down. It is going to damage. Clear? Now let us move on to the LED. What is LED? That we are going to study now. LED stands for what? Light emitting diode. LED also diode. But here what is going to be happen? Light is emitted. Right? Whenever our electrons are moving, right? Whenever our electrons are moving from one band to other band, what is going to be happening? Photons will release, that too in the form of what? Light energy. Right? All these things we are going to study in our next slide. Now, LED stands for what? Light emitting diode. It is most widely used semiconductor which emits either visible light or invisible infrared light when forward biased. Please remember that our light emitting diode is going to work under forward bias condition only. Whenever it is reversed bias or if you give reverse voltage, then what is going to happen? Your LED is going to be damaged. Clear? Now what in our houses we have televisions, right? For that we use remote controls, right? These remote controls has what? LEDs which will generate invisible light. Clear? Here it is mentioned. Remote controls generate invisible light. Now here light emitting diode means which converts electrical energy into light energy when voltage is applied. Now on left hand side we can see the normal diode as well as light emitting diode. This is the symbol. The above one is the symbol for what? Normal diode, and the below is the symbol for what? Light emitting diode. On our right hand side we can see the practical light emitting diode. This is how our light emitting diode is going to look like in our laboratories or in our practical scenario. Now in our light emitting diode also we have regions, N-type, P-type and depletion layer. All these things in LED also present. But here we need to understand one thing. Our LED is just like a normal PN junction diode. But here the difference is PN junction diode is made up of what? either silicon or germanium. But this is not in the case of LED. LED is made up of what? Gallium arsenic or gallium arsenic phosphate. Now, this is what makes the difference. This is why we are going to see the light whenever our light emitting diode is in the forward bias condition. How it is going to be happen, that we are going to see in the further slides. Now here we can see. In forward bias, energy is released in the form of light when free electron conduction band recombines with the holes in the valence band. Clear? Whenever a free electron conduction band is combines with hole in valence band, this process is called what? Electroluminescence. Right? Whenever it is combining, it releases the energy in the form of what? Light. This process is known as what? Electroluminescence. Right? As I said, like a normal PN junction diode allows electric current only in one direction, LEDs also operate only in forward bias condition only. The N-type material should be negatively charged and P-type material should be positively charged to create a LED. Right? As a PN junction, we have P-type and N-type, right? In the same way, in LED also we have P-type and N-type, where the difference is here our LED is not made up of silicon and germanium, where our LED is made up of different material. Gallium arsenic, gallium arsenic phosphate, and there are different materials are present to design a LED that we are going to see in upcoming slides. Now here we can see the layers of LED. I said P-type semiconductor, N-type semiconductor depletion layer is right, that we can see here. Now there are 3 layers in light emitting mode. That is, these are P-type conductor, trivalent impurities added to the intrinsic or pure semiconductor. Holes are majority charge carriers, yes, just like a PN junction diode. In N-type semiconductor, pentavalent impurities are added to the intrinsic semiconductor. Free electrons are majority charge carriers, just like a PN junction diode. Here we can see the depletion layer or region. It is a region or layer between P-type and N-type semiconductor where no charge carriers present. Right? What do you mean by depletion layer? We have studied in our first class. The region where absence of free charge carrying particles are present. Clear? The region where you will not find any charge carrying particles. That region is known as depletion layer. And this also, we have a depletion layer where we will not find any free charge carrying particle. That is what mentioned. It is a barrier to current. Yes, whatever we know about depletion layer, that is same present here. It just acts as a barrier to the current. To overcome this barrier, we need to apply voltage which is greater than the barrier potential of this layer. Yes. What is the barrier potential of PN junction diode? We have studied in our first class, right? What is it? 0.7. So once we should give the voltage which exceeds 0.7, then your PN junction diode is going to be conduct. Same case is present for our light emitting diode also. So to overcome this barrier, what we need to do? We need to apply voltage which is greater than barrier potential of this layer. Clear? Here we can see light emitting diode LED works only in forward bias condition where free electrons are from N side and holes from P side are pushed towards the junction. Right? The recombination of free electrons and the holes takes place in depletion region as well as in p-type and n-type semiconductor, right? Now let us move on to the next slide. Now this is how we can visualize the LED. Hence, each recombination of charge emits energy in the form of light. The brightness of the emitter light depends upon the material used for conducting LED and forward current through the LED. Right, this light depends on what? Materials which we have used and current flowing through the LED. Here in the diagram we can see p-type we have positive, that means anode, and n-type is nothing but what? Cathode, means negative. I used a battery, plus is connected to p side and minus negative terminal is connected to my n-type. Whenever I am giving in this format, right, p side holes are pushed towards the depletion region and n side free electron are pushed towards p-type material, because I have given negative, right? So here what? Electrons are present, these are pushed towards p-type material and pushed towards the depletion area. Whenever these are moving, what is going to be happening? Our electrons are going to recombine with what? Recombine with what? Holes. Right. Whenever it is recombining, what is going to be happening? Light is emitted. You can see here. Right. Whenever this electron, say this is the electron moving, this is moving, and here one hole is there. When it is recombined here, then energy is released in the form of what? Light, right? Now in the form of light it is emitted, right? This is why I am calling this type of diode as what? Light emitting diode. Clear? As light is emitting, we can see the emitted light. Whenever our electron is going to combine with hole, we can see the light with our eyes. So that is why this is known as what? Light emitting diode. This phenomena, whenever electron is combining with the hole, light is generated. This phenomena, or converting electrical energy into light energy phenomena, is known as what? Electroluminescence. Clear? Now we have one small video. Let us see that video so that it will be easy for us to understand how this is happening. Clear?
In simple terms, here's how an LED works. An LED is a basic semiconductor device. P-type semiconductor material containing positively charged carriers called holes is combined with N-type semiconductor material containing negatively charged carriers called electrons to create a diode. When a current supply is connected to the diode, the negative charged electrons are forced to move one direction, and the positive holes move in the opposite direction. When a free electron comes near a hole, it combines with the hole. The holes exist at a lower energy level than the free electron, so the electron must lose energy to combine with the hole. This energy is released in the form of a photon, or a unit of light. The amount of photon energy released determines the frequency or color of the light. The type of material and process of creating the N-type and P-type materials dictate the color of the photons, as well as the efficiency and other performance characteristics of the LED. After processing the material into an LED chip, the chip is installed in a package that allows electrical connection and directs as much light as possible in the desired direction.
Now here we can see when positive is combining with negative, or else when electron is combining with hole, we can see energy is released in the form of light. We can see in this video. Right? Whenever it is combining, energy is released in the form of what? Light energy. That is what we have seen in this animation.
The electron must lose energy to combine with the whole. This energy is released in the form of a photon, or unit of light. The amount of photon energy released determines the frequency or color of a light. The type of material.
Now here we seen how light is generated, how light energy is generated when electron is combining with the hole. Clear? Now let us move on to the next slide. Now here we can see, in normal silicon diodes, energy gap between conduction and the valence band is less. So low energy photons are released with low frequency and invisible to human eye. Okay. Whereas in LED, energy gap between conduction and valence band is very large, so high energy photons released and visible to human eye. And in LED, because of the material also, we are going to see the intensity of the light, right? Here we can see, since LEDs are operated only in forward bias condition, so if reverse bias voltage is applied to LED, it may be damaged. Yes, I have said right. Whenever if you're going to give voltage in reverse bias condition, it may lead to damage of our LED. Clear? LEDs can switch on and off at very fast speeds of nanoseconds. Right? The most commonly used colors of LED are green, red, orange and yellow. We can see here. The most common colors of LEDs are, what are those? Green, red, orange and yellow. But schematic symbol of them are same. Whatever the color may be, the symbol of LED remains the same, which we have seen in our previous slide. Clear? Now here we can see the biasing of a LED. The forward voltage and current of most LEDs from what? 1 volt to 3 volts, and current is of 200 milliamp to 100 milliamp respectively. Clear? To avoid destruction of device because of more voltage, we need to place a resistor, that is RS, in series with LED. Now when you give sudden voltage to our LED, there may be a chance of damaging our LED. So what we need to do? We need to place a resistor, right? So that our LED will not be damaged, which is placed between LED and source voltage, that is Vs, and this resistor is called as current limiting resistor, right? To avoid destruction of a device, what we are placing? A resistor in series with LED, right? This resistor is known as what? Current limiting resistor. You can see here. To avoid destruction of device because of more voltage, we need to place a resistor RS in series with LED, which is placed between LED and voltage source Vs, and this resistor is called as current limiting resistor. So we can protect LED from damage by using the current limiting resistor. Clear? Now here we can see the current, forward current through the LED by this formula. The current flowing through LED is mathematically written as what? IF is equals to Vs minus Vd by Rs. What is Vs here? Source voltage. What is Vd here? Voltage across the diode by Rs. What is Rs here? Yeah, the resistor which we have connected in series. Where IF is forward current, right? Vs is the source or supply voltage, VD is voltage drop across our LED, R is the resistor or current limiting resistor. Yes. The amount of output light emitted by LED is directly proportional to the amount of forward current flowing through it. Right. Now we already seen the limit, right? 3 volts, right? If we give less than 3, what is going to be happen? Yeah, what is going to be happen? Now 1 to 3 volts, right? Whenever you will give less, what is going to be happen? It will not glow, right? That is what's mentioned here. The amount of output light emitting by LED is directly proportional to what? The amount of forward current flowing through it. Clear? Now, here are the different types of LEDs which we can see. There are two classes of light emitting diodes. These are visible LEDs and invisible LEDs. Right? Visible LEDs are there, invisible LEDs are there. Also, the wavelength or color of emitting light depends on the forbidden gap or energy gap of the materials. Right? Light, wavelength, color depends on what? The forbidden gap between these materials, right? Here down we can see the different types of light emitting diodes. That means different materials we can see, right? Now first one we can see gallium arsenide. Gallium arsenide light emitting diode gives what? Infrared. Gallium arsenide phosphide GaAsP. What is the color? Red to infrared, orange. Aluminium gallium arsenide phosphide. What it will give? High brightness red, orange and yellow. Now this is the color emitted by this LED. Aluminium gallium arsenide phosphide LED is going to give which colors? High brightness red, orange and yellow. Now next one is gallium phosphide GaP. It will emit which color? Red, yellow and green. Aluminium gallium phosphide green. Gallium nitride green, emerald green. Gallium indium nitride what? Near ultraviolet, bluish green and blue. Silicon carbide what? Blue as substrate. Zinc selenide what? Blue. These are the different types of LEDs and this is the colors emitted by our LEDs. Clear? Now let us see the applications of our LEDs. Generally our LEDs are widely used in nowadays. Clear? Let us move on to the next slide where we can see the types. Where we can see the applications of LEDs in a wide space. Now, these are the applications of LEDs. LED can be used in where? Burglar alarm systems, traffic signals. Yes, we can see in our daily life where LEDs are used. Every day when we are going out, we can see the traffic signals where our LEDs are used. And we have mobile phones, right? In that we have camera flashes. That also you can see white color LED you can see there. Now it is used in aviation, lightning, railway signals. For railway signals also our LEDs are going to be used. And it is used in calculators. Presently we know LED TVs are present, right? Here itself mentioned light emitting LED TVs. So widely our LEDs are used. In our 7-segment display also LEDs are used. Digital watches are there. There also LEDs are there. Right, in digital watches we can see LEDs where the digits are visible to us. Clear? All these are applications of LED. Apart from these, there are many more applications of our LEDs. Clear? Now let us recollect the topics which we have covered today. What are the topics which we have covered today? Zener diode, basic characteristics of Zener diode, avalanche breakdown, why Zener is special compared to our PN junction diode, and next one, light emitting diode, construction of our light emitting diode, and what are the layers of light emitting diode, and how light is emitting when our electrons are combined with holes, right? And we also seeing what are the how our light emitting diode is going to be biased, and we are seeing what are the applications of LED. All these things we have studied so far. Thank you.